We've spent the entire semester looking at Earth's past. Now it's time to look at its future. We'll start by looking at the relatively near-term future, a few 100 million years or so. And as the tectonic plates reshuffle, we'll get Pangaea Proxima, the next Pangaea. And this would be the configuration we think that would result with the closing of the Atlantic Ocean. But that's only a few 100 million years in the future. We're about farther into the future. Well, ultimately, the fate of the sun and its evolution controls what happens here on Earth. And so billions of years down the line, the sun's going to evolve. That will probably end life and geologic history on Earth. The red giant phase may envelop the Earth, may totally vaporize it, but really that's the end of the planetary history for Earth. The sun will shed its outer atmosphere and form a planetary nebula, and the star that remains behind will be a white dwarf, and it will stay like that for trillions of years into the future. Let's start big and talk about the future of the universe. So just as we talked about how it all started with the Big Bang, there are several models that deal with the evolution and end of the universe. The creation model is, of course, the Big Bang. This is our current idea of how we think the universe began, expanding from a singularity about 13.8 billion years ago, and the universe has been expanding ever since. During this time, stars have been forming and will continue for trillions of years into the future. It's called the Stelliferous era, what we're living in right now, right at the beginning of it actually, only a few billion years into it. But where is it going? The ultimate end is unknown. There are several models that deal with this. Currently, we're looking at dark matter and other variations on the expansion of the Big Bang, how fast it's expanding, whether it's accelerating, getting farther and farther apart, or whether there's enough matter to stop the expansion and pull everything back into what's called a big crunch. So there's different ideas on how this will go, and it's all theoretical cosmology. Plate tectonic processes have been operating on Earth since way back in the Hadean, and it's all because of the heat energy within the planet, and there's been enough heat energy to drive mantle convection, to drive the various plate tectonic processes like subduction, and it's thought that this will continue for another billion years at least. So when trying to predict what's going to happen in the future, we have models, and the models are based on the present location of the plates, their direction and rate of movement, and as with any models, the farther you go into the future, the more uncertain they become. And with these, past a few 100 million years, things get pretty tenuous. But that won't keep us from speculating. As we've discussed, there have been several supercontinents of the past, and there seems to be a cycle of creation and breakup of supercontinents. Pangaea was the last one, and it broke up about 200 million years ago in the early part of the Mesozoic. It's been a few 100 million years, and we think a few 100 million years in the future we're going to have a new one. Ballpark 250 million years into the future, there probably will be another supercontinent. And there's two real variations on what it's going to look like. And they deal with either closing the Atlantic Ocean basin or closing the Pacific. One model is called Pangaea Proxima. Pangaea Proxima, that means the next Pangaea. And this involves closing of the Atlantic Ocean basin, and that would involve lengthening of the Scotia Arc and the Lesser Antilles Arc and destruction of the Atlantic Oceanic Plate, and it would bring North America and South America into contact with Eurasia and Africa. So this is the configuration we think that Pangaea Proxima would take on. Another name for Pangaea Proxima is Pangaea Ultima, but it's fallen out of favor because Ultima means ultimate, like the last one. It's not certain whether this is going to be the last one. This is definitely going to be the next one, so Pangaea Proxima is the name for this model. The other model is where the Pacific Ocean basin closes, and it brings Eurasia, North and South America together. And that's these two, and they're very similar in form. One is called Amasia, and the other one's called Novo-Pangea. So this is several hundred million years into the future, and there are things that need to happen for either one to occur. Okay, so closing of the Atlantic to give you Pangea Proxima, or closing of the Pacific to give you Amasia or Novo-Pangea. Of course, then we will be able to play Risk based on Pangea Ultima in this case. You never know what you're going to find on the internet. So let's look at one of the models and how it evolves into the future. And this is for Pangea Proxima. This is the configuration of continents for 50 million years into the future. The Western Hemisphere looks very similar. The main difference is there's now a subduction zone all along the western margin of the Atlantic Ocean basin. Right now there's just the Scotia Arc and the Lesser Antilles Arc. And so what's happened over 50 million years is each one is lengthened and they've actually connected, and now the North and South Atlantic oceanic plates here are subducting underneath North and South America. So this is closing the Atlantic Ocean basin. You can see Africa has completed its collision with Eurasia. Antarctica is still pretty much down on the South Pole, and Australia is in a similar position. Another 100 million years, and the Atlantic has decreased in size significantly. The South Atlantic and the Indian Ocean now are combining into one large ocean basin. And there, of course, is the Pacific out there. And then another 100 million years later, now to 250 million years from now, gone is the Atlantic Ocean basin. The remnant of the Southern Atlantic and Indian Ocean has been wrapped up there, and North America and Africa are coming together with South America, with Eurasia. So this is Pangea Proxima. And of course there's Australia and Antarctica, never very far apart. They are twinning down there near the pole. This is the Pangea Proxima model from 50 million, 150, 250. Well, we know there's a relationship between plate tectonics and magmatism and volcanism. Some of these relationships are short-term and some are more long-term in terms of Earth's history. Things like flood basalt eruptions occur typically over long periods of time. They haven't occurred in human history. They're relatively spaced out in Earth's history, and they're relatively short, only a few million years in length. So they're short events relative to Earth's geologic history that occur over long periods. And we've seen this graph before, which shows the major flood basalt events. There have been several flood basalt eruptions, not all of which result in mass extinctions, but usually some modification of the climate. The Siberian traps, the Camp eruption at the end of the Triassic, several flood basalt eruptions during the Mesozoic, the Deccan eruption in India, the Columbia River flood basalt eruption. So this cycle is probably going to continue. There will be a next one. And what will its effects be on the Earth? Probably quite similar to the effects of the previous ones. Oceanic plateaus giving oceanic anoxic events, changing the chemistry of the oceans, flood basalt eruptions, modifying the atmosphere. So these are long-term volcanic events, but there are short-term events that are going on all the time. And on the whole other end of the volcanic scale, from flood basalt at one end to supervolcano caldera eruptions on the other. So these occur over time spans of thousands or millions of years and are quite frequent in terms of Earth's history. And just in the last few million years, there have been several major caldera-style eruptions. 3 at Yellowstone within the last 2 million years or so. The largest one is something called Toba, and that was in the southwestern Pacific, and that erupted maybe 75,000 years ago. And there is debate on whether that actually affected human evolution. Here's the Snake River Plain. We see the progression as North American plate moves over the Yellowstone mantle plume, and we can see the age of the volcanics, and here's Yellowstone, probably going to erupt again. And given that the Huckleberry Ridge eruption was 2.2 million years ago, and the two younger ones were at 1.3 and 630,000, means we're pretty much dialed in for another Yellowstone eruption. So these kind of eruptions will keep occurring in the short term into the future. We are living in an ice age, and the glaciations that we've been experiencing the past few million years will continue for some period of time at least. To estimate where we're going with this ice age, some people have taken the data from the ice cores and looked back in the last million years or so and constructed some models based on orbital data to match their Milankovitch-based model with the existing data. And you can see they have a pretty good match there of the model with the existing data. The point of this is they're using their model to extend into the future. And so here is their model into the past. Here is the present. You can see the cold glacial cycles, warmer interglacial. Here are the last two glaciations. The glaciation itself is much longer than the shorter interglacial. Then the last Wisconsin glaciation lasted for tens of thousands of years, and then roughly 12,000 years ago came out of that very quickly. And it's thought that this interglacial will only last 10 or 20,000 years. So right now we are more or less at the peak of this interglacial, and this model says we will be heading on the downslope here for the next 60,000 years towards some glacial maximum, temperature minimum. And then after some period of time, we'll experience another interglacial, which will last about 20,000 years after that. So that is the model. It's continuing the glacial cycle that we see now. Why should it stop? What's going to stop the ice age? There might be some modification of these curves a little bit, but this more or less shows a similar pattern as to what we've been seeing for the last several 100,000 years. At some point, of course, the ice age will end, but we don't think we're anywhere close to that. Exactly when we begin this downslope, there's uncertainty with that. When this next glaciation will actually begin, we've never lived through that change. That was 11 or 12,000 years ago. Some think that we could be heading into it as we speak. There's a lot of argument about this topic, climate change. But that's what the climate's doing. It's changing. And it's inevitable that it's going to cool off and we will descend into another glaciation. Probably hundreds to thousands of years, not millions of years. Let's talk about the climate now. We're in an ice age now and we will eventually come out of it. But then what? Well, it's cold now and it will eventually warm up. But over a much longer period of time, the major change to our climate is going to come from the amount of carbon dioxide in the atmosphere. And what's been going on throughout the last 500 million years is CO2 has been decreasing, and it will continue to decrease into the future. This graph right here shows what we think temperature and carbon dioxide was like into the past. And we've discussed these kind of graphs before and analyzed the patterns and why they occur. But if you remember, back in the early Paleozoic, in the Cambrian period, carbon dioxide levels in the atmosphere were thousands of parts per million, ppm, 7,000 ppm or more, and it's been decreasing ever since. Of course, there's some deviations, some ups and downs, but there's been this general decrease to where we are now at about 300 or 400 ppm. So from thousands of ppm 500 million years ago down to 400 ppm now, and it's going to continue. So why would this change all of a sudden? So this is going to continue, and it's thought that it's going to reach a point within at least 600 million years, maybe before, where CO2 concentrations will be so low that certain types of plants will have trouble photosynthesizing. And these include what are called the C3 plants, like wheat and trees and such. And these represent the bulk of Earth's biomass. 95% of Earth's current biomass are plants that use the C3 photosynthesis. And it's thought that the rest of the plants, which conduct other kinds of photosynthesis we call C4, grasses, corn, things like that, well, they're going to struggle a few million years later. So 600 million years, the C3 plants, and then at about 800 million years in the future, the rest of the plants will be gone. There won't be enough CO2 for them to photosynthesize. And without photosynthesis, where's the oxygen going to come from? The free atmospheric oxygen will be depleted, and that means the ozone layer will also. So this is the major change, and this isn't billions of years into the future. This is within a billion years or so, and it's only a few hundred million years out, and it's a catastrophic change. In terms of life, there are certain life forms that have been around since the beginning, and they won't care what the plants are doing and what the oxygen is. And so those extremophiles will continue living in their various exotic habitats. But for multicellular life that mostly depends on carbon and oxygen, it's going to be a real struggle and probably the extinction of multicellular life on Earth within a billion years. One other factor relating to climate is the influence that the moon has on the Earth. The Earth is the only terrestrial planet in the solar system with a significant moon. Venus and Mercury have none. Mars has two little pathetic captured asteroids. Okay, so Earth has a significant mass out there called the moon. And throughout Earth's history, the moon has exerted gravitational influence on the Earth, creating tides and such. But one thing that it has helped with is stabilizing the tilt axis of the Earth. And so it really limits the Earth from wobbling too much over time. We know that any slight variation of the Earth's tilt will give climatic shifts. And the more you change the tilt axis, the more you're generating differences in solar radiation on the Earth, and that just plays havoc with the climate. So the moon has been a real stabilizer in that regard. One thing that's happening is the moon is getting slightly farther away. There's been a tidal effect of the moon pulling on the Earth and slowing it down. The gravity is greatest right underneath the moon, but the tidal bulge keeps rotating. These are basically the oceans, and the Earth rotates underneath the high part of this bulge twice a day. So that's why we have high tides twice a day. You can see the bulge is a little bit forward of the position right under the moon, and that's because the centripetal force has carried it farther. You can't just stop that mass right there because that bulge too is rotating. While the moon is trying to pull back on it, and as that happens, it's slowing the Earth's rotation down. It's like a drag. And so that's why the Earth used to be spinning faster hundreds of millions of years ago, and it's been slowly slowing down. We used to have over 400 days in a year. Now we only have 365. This has not just decreased the spin rate of the Earth, but also it has stabilized its tilt axis. Well, as the moon slows down the Earth's spin, conservation of angular momentum means it has to move farther away. So the moon is actually moving farther away from the Earth all the time. And it's at a measurable rate of a few centimeters a year. So it's going to get to a point in a few billion years, anywhere from 1.5 to 4.5. Nothing like a tight age constraint there. But in a few billion years, the moon's going to be far enough out that it won't really be a factor in stabilizing Earth's tilt. With no stabilization factor there, what's going to happen with the Earth's tilt? Is it going to vary more? Is it going to wobble much more? That is probably something that's going to happen, the degree of which we don't know. This is, of course, long after the climate has changed from the decrease of carbon dioxide. One thing to note with these models as we project into the future, it has nothing to do with evolution of intelligent life on Earth. This is just strict modeling of these different processes into the future. The sun is the #1 determining factor in what kind of climate we have here on Earth. And it's thought that the energy output of the sun has been growing at a constant rate over geologic time, specifically about 10% over about 1 billion years. So we think the sun is growing brighter about 10% every 1.1 billion years. What that translates to is relative to today's sunlight, the sun would have been 10% dimmer back in the Mesoproterozoic during Rodinia time. That's a significant amount of sunlight. It also means that 1.1 billion years into the future, the sun will be 10% brighter. The surface temperature on Earth is going to be a lot more than it is today. In fact, the mean surface temperature will be about 116 degrees Fahrenheit. Today it's about 59 degrees Fahrenheit. We know that right now 59 degrees is the mean. There are places that are much colder in Antarctica. There are places that are much warmer in many arid regions and deserts. Phoenix gets to about 116 for a few days during a summer. This is the mean temperature. So this is 50, 60 degrees warmer than today. That's about 1 billion years into the future. So that is going to have a drastic effect over time. It's a long, slow change. It's nothing that's going to be immediate. But the liquid water on Earth is going to dry up and Earth will become a desert. Free water, like lakes and streams and oceans, will begin to disappear. And that water vapor will be in the atmosphere. And so if multicellular life was having a problem before, the rest of the life forms are going to be having a problem now. And so, of course, there'll still be extremophiles that will be able to deal with this, but it's becoming harder and harder for life to function in these more extreme environments. Most life on the planet, other than extremophile life, will be extinct by this point. So we're about 1 billion years out. Earth will become a desert on a global scale. And if you project this into the future, the sun progressively gets brighter and brighter. It's thought that the atmosphere could become so thick and we could get some kind of runaway greenhouse effect, more or less like what Venus is like today. So a greenhouse Earth 4 billion years from now. That's much farther into the future. Of course, a few billion years farther down the road, 5 or 6 billion years from now, the Earth will be put out of its misery. As the sun goes into its red giant phase, the atmosphere of the Earth will most likely be destroyed, and possibly the entire Earth as well. It just depends on exactly how large the red giant phase gets, whether it gets out to the orbit of the Earth or not. If it does, then Earth will be partially or maybe even totally vaporized. So this is the future of Earth in the next 5 or 6 billion years. Right now we are living in the middle of this geologic history, and from what we've talked about, advanced life has only been present for a short window of time in Earth's history. Multicellular life and advanced life really within the last 600 million years or so, and now it will continue for a few 100 million years more. So 1 billion years maybe of Earth's history will have advanced life. After the next 1 billion years or so, the conditions are just too drastic for life to exist. Well, what else do we have coming up in the future? Here's one. We think that in 1.5 million years from now, a red dwarf star called Gliese 710 will pass within a light year of Sol, the sun. A light year is pretty far out. It's much farther than the planetary system of the 8 planets. But it's still close enough that it will pass through the outer part of the solar system known as the Oort cloud, which is the region of icy objects, and it could destabilize orbits of some of those objects and fling some of the objects out and also fling some of the objects in. Could this generate more impacts, this kind of event? There's a lot of speculation about this, but it's not thought to be a significant impact hazard, but it is possible. What else do we have? 100 million years into the future, statistically speaking, we'll probably have been hit by a large asteroid, most likely, maybe even a comet. Earth is being impacted all the time. Particles are very small, are impacting Earth all the time, every hour, every day. But The larger the chunk, the less frequent the collision. Something that's fairly large in terms of kilometers in size, that only happens every few millions of years or so. But they do happen. So it's thought that we'll have a large impact by the time we get to about 100 million years down the road. Would this be enough for a mass extinction? It's quite possible. The life forms of the future are really going to have a lot to deal with in terms of the climate and these other threats. Of course, in about 4 billion years, the Milky Way itself is going to collide with the Andromeda Galaxy. And this is interesting because the Milky Way is part of a local group of galaxies, and it and the Andromeda Galaxy are the two biggest ones. And they are drawn to each other. The two most massive galaxies are drawn to each other. This is an interesting sequence which shows the relative size of Andromeda today in the sky. Here's the Milky Way galaxy if you're looking at the horizon there. That's the Andromeda Galaxy. And then with time, as the Andromeda and Milky Way galaxies get closer, this would be the size of the Andromeda Galaxy in the night sky. And then even closer here. And then the collision would ensue and ultimately do this little cosmic dance, and both galaxies would deform and mix together and form one big, it's called elliptical galaxy. And this would take quite some time. And this isn't like two freight trains colliding, because both objects are made of stars that have a lot of space in between. But the gravitational changes and it would just be chaos. But this is 4 billion years down the road. Well, that's pretty much the future of the Earth. I know it seems pretty bleak, but what about the sun? Because really the sun is the main driver of the history of the solar system. So let's look ahead to what the future holds there. This infographic here shows the evolution of different types of stars. There are very massive stars and less massive stars as you go this way. Depending on the mass of the star and the temperature, we can classify them. And the hotter stars have colors that are bluish in color, and then down to white. As they get cooler and cooler, they become yellow, and then orange, and then red. So that's why we typically call these red dwarfs. The sun is a yellow-white type of star, and then as you get into the more massive stars, they become much more bright and much more white and blue. Most of the stars in the galaxy are red dwarfs. Probably 80% or more of all stars in the Milky Way are this kind of star. Very small. You can see they evolve over a long period of time, and they don't change much. They just don't have enough mass to change. That's the main deal with why there's differences in the evolution of these stars, is the mass. Low mass stars, they are constant over trillions of years. The high mass stars are very unstable. They live a fast and furious life, and over the course of a few million years go through their life cycle and then explode as a supernova, or even eventually collapse into a black hole. But then there are stars like our sun, and these are ones that are stable for billions of years. They're not going through supernova events. There's not enough mass for that to happen, so the sun's never going to go supernova. It's never going to collapse into a black hole. But what will happen down the road is that it will expand into what's called a red giant, significantly bigger than it is today, expanding out past the orbit of Mercury, out past the orbit of Venus, and possibly out to the orbit of the Earth. So a huge, tenuous ball of gas here, and as it expands, it envelops this bigger volume, it'll cool, and that's why it gets a red color. So that's called a red giant. This phase might last maybe 1 billion years, and then the outer atmosphere of the sun will keep expanding away, forming what's called a planetary nebula. And that will pass through the solar system outwards in all directions. Very pretty astronomical object as we see them around the galaxy. But what's left behind is the remnant of the former star, and that's called a white dwarf. And this white dwarf will remain stable for trillions of years. So this is where the sun is today. This is its future. Let's look a little bit more closely at the sun and its evolution. Our parent star is called Sol. That's the sun's name. And it's a certain class of star called a G-type star. There's different types of stars, small ones, low mass stars, large ones, high mass stars. The sun is kind of in between, relatively low mass, but small, dim, M-type red dwarfs. Here's the sun, which is a yellow-white G-type star. And then as we get into the more massive stars, they become bigger and brighter, whiter and bluer in color. This is a diagram here that's used to describe the distribution of different kinds of stars and their evolution. On the horizontal here, we have temperature from cooler to warmer. So a few thousand degrees K to tens of thousands of degrees K. So cooler here, warmer here. The vertical scale here, this is luminosity or brightness. And it's all relative to the sun. And notice this is a log scale. Any star with the brightness of the sun would be here. Anything down here below is dimmer. Everything above that would be brighter. The small stars, which are cool, called red dwarfs, they're very dim. They plot down here. The orange stars, which are a little bit more massive, a little bit brighter, a little bit hotter, plot here. Here's where the sun plots. A little bit more white stars are brighter than the sun, a little bit hotter, and then we get into the massive stars, which are very hot and very bright. So it explains the distribution of stars. And this line here is called the main sequence. Small low mass stars, which are very dim, large high mass stars, which are very bright, and then there's the sun kind of in between. So this main sequence here is where stars live the bulk of their life. Towards the end of their life, then that's when we see changes in some stars. But the main sequence is the time of stability for a star. And so for stars like these red dwarfs, very low mass stars, they stay in the main sequence almost their entire life. They are very stable and they will never really leave the main sequence. These high mass stars only remain on the main sequence for a short period of time, and then they begin the chaotic evolution into supernovas and then possibly even black holes. But stars like our sun stay on the main sequence for billions of years before they undergo any change. Here's what sun's history has looked like. 4.5 billion years ago it formed from the solar nebula, and it's been increasing in brightness very slowly ever since. Here we are today. 4.5 billion years have passed. It's going to continue doing that for billions of years more, and it's going to stay on this main sequence here where it's very stable, period of stability for our star. So we're right in the middle of that main sequence phase. As the sun continues to evolve along the main sequence, eventually it's going to undergo changes with its amount of hydrogen that it's fusing in its core. Well, eventually it's going to run out. And this will cause it to leave the main sequence, and it will then enter the red giant phase of its life. After about 10 billion years or so on the main sequence, it'll run out of fuel and then eventually swell up into this red giant star. That's in another 5.5 billion years. Here we are right in the middle of this main sequence. In about 5 or 6 billion years, the sun will go red giant. On this diagram that we were just looking at, the sun's sitting on this main sequence for 10 billion years. When it goes red giant phase, it's going to balloon up many times its current size. And as it does that, it's going to cool off and it'll turn from yellow-white to red in color because it's encompassing so much more volume, and it'll cool off. As it cools off, it's got to move this way, but as it gets bigger, it gets brighter. So it starts to move this way, and this is the red giant portion of the diagram. And there's a bunch of different events that could occur, but the bottom line here is as the sun expands into a larger red giant, it gets brighter and cooler. The red giant portion of the diagram, a few hundred times bigger than it is today, cooler and redder. This is the sun as a red giant. This is relative to its size today. It's much bigger. So again, it's going to expand out past Mercury and Venus for sure. And it'll stay in this situation for about 1 billion years or so. So it's a relatively short-term state that the sun's going to be in, being a red giant, before it transitions into the next phase. So after about 1 billion years of being a red giant, roughly 6.5 billion years from now, various changes will be going on within the star itself, and its outer layers will expand outward, forming what's called a planetary nebula. And this process is fairly rapid. It only takes a few thousand years or a few tens of thousands of years relative to the millions and billions we've been talking about. This end of the red giant phase into the planetary nebula phase is fairly quick. 11 billion years into its life, this is happening. Main sequence for 10 billion years, red giant for another billion. Here we are at the planetary nebula stage, about 11 billion years. Here we are right now, 5.5 billion years, it'll be red giant, and in 6.5 billion is when we'll have this planetary nebula phase. On this diagram here, again, remember the main sequence is where the sun was for billions of years, and then as things changed within its interior, it ballooned up into a red giant, which is cooler and brighter, so this area right here. But then after a while, the red giant phase would end and we'd move into the planetary nebula phase, basically where the atmosphere is moving out and expanding. So after this, what's left behind, the remnant of Sol, is a white dwarf. And that will become stable and continue to burn as a star for billions of years. Much smaller than the previous star. White dwarfs are on the size of terrestrial planets. They're much smaller than your typical star, but they are very stable and they will continue to shine for billions of years, eventually running out of energy, turning into what's called a black dwarf, but that's way down the line. So gone from main sequence to red giant to planetary nebula, eventually to white dwarf. So white dwarf, as I said, is on the order of the size of a terrestrial planet like Earth. The black dwarf won't be shining at all. Well, what about the planets? What about Earth? Looking at the present configuration of the solar system, there's what's called a habitable zone, specifically a circumstellar habitable zone. Circumstellar means around a star, so it's a zone of orbits where water is stable in the liquid phase across much of the planetary surface. So we know that's the case on Earth, right here in the inner half of the habitable zone. Mars is right at the outer edge of the habitable zone. Most of the water is frozen there, though, so there's not a whole lot of liquid water on Mars, so it's right on the edge. Venus has no liquid water whatsoever. It's on the inside of the habitable zone, as is Mercury. So the Goldilocks zone is what this is called. Too hot here for water. Everything out here, it's water ice. Here, the temperatures are just right. So that's right now. In the future, as the sun enters its red giant phase, it's not only going to grow in size, but it's going to increase in its luminosity and its energy it's putting out, and it's going to push this habitable zone farther out. And so what was habitable is no longer habitable. The Earth and Mars will no longer be within the habitable zone. It would just be too warm. Planets like Jupiter and Saturn will be now within this habitable zone as long as the sun is in this red giant phase. So for about 1 billion years or so, this expanded habitable zone will exist. And while these are gas giant planets, Jupiter and Saturn, their moons are largely water ice. And so what does this mean for them? And so they're within the habitable zone. It's quite possible that there will be large amounts of liquid water at the surface of these moons. So what does that mean for life? Whatever it means, life only has about 1 billion years to figure it out. Because after the red giant phase, the planetary nebula occurs, and then the sun shrinks down to white dwarf, and this habitable zone will then collapse. So since the sun has been stable for billions of years, the habitable zone has been stable for billions of years. and it's allowed life to occur on our planet. It's given it the ample time necessary for various evolution and mutations to occur. When it expands out this far, that time period is going to be compressed to only about 1 billion years. This habitable zone, the one we're in now, will have existed for about 10 billion years. The red giant habitable zone for only about 1 billion years. To finish this discussion, here is the current state of the habitable zone in the solar system, with Earth in the inner half there. During the red giant phase, this would change and the circumstellar habitable zone will expand into the outer solar system. The G-type main sequence stage we're in now will give you a circumstellar habitable zone in Earth's orbit, so a watery Earth. But then with the red giant phase, that's going to move farther out and we'll have red giant Sol circumstellar habitable zone, and this will be one of the moons of Jupiter or Saturn, watery moons. And so it's in this environment in which organic life might develop on these formerly icy moons. And then as the sun evolves into a white dwarf, the circumstellar habitable zone will collapse and eventually cease to exist. So everything will freeze after that. For billions and billions and trillions of years afterwards, the sun will be in its white dwarf phase, too cold for any kind of life to exist. The real window of habitability for the solar system is the few billion years we're living in right now.